Share screen. Start video. It says start video. Nicholas. Hola. Nicholas Dark is connecting to audio and can't hear you yet. Well, can you hear me now? Earth calling Nicholas, Earth calling Nicholas. Come in, Nicholas.
Hey.
Hey, hey, hey. I wonder if we'll have any other customers. Oh, there's Dawn. I think I see Dawn. Yeah, hey, Dawn.
How you doing, sir?
Doing good. Now, don't I need to click on that to get the whiteboard? I want my whiteboard. Oh, look, there's Abdullah's coming in. Mark is coming in. Miranda's coming. We're getting some customers here.
Hello.
Hello. Jackson.
No.
It's almost time, in about 3 minutes. Oh, look at all these wonderful students here. Look at here. Coy and Kerman. Guys, this is my daughter, Susanna. She's helping me. Without her and my other daughter, I would be in big trouble. There's Jack.
There we go.
There's an important person. Hey, look at there. How did you do that? Did you click on that? Is that what you... Good. Excellent. Okay. I like it when they have all their names over here. I don't see that yet. Yeah, there's some more.
There we go.
I feel like my room is a mess.
Mine too, yeah.
There's
I guess when you go down through the list, it shows, like when you go up and down, it shows everybody.
yeah, pretty good crowd. Oh yeah, there's an important person.
Okay, so then you can see yourself there, right?
Yeah,
okay.
and I'll need to tilt this like that.
There we go.
That's pretty good. Yeah. It is approximately 1 o'clock, and I think what I want to do is unmute everybody. Let me do that. So come over here. I don't want to click end meeting. That would be bad. I don't see where it says mute.
I think that they have theirs set on mute.
Yeah.
I don't think it's you setting them on mute.
Oh, okay.
As long as everybody mutes their own, which people usually do.
All right, and it's recording.
It's recording.
That's good. Okay, well, it's 1 o'clock. I guess I'll launch into the fascinating topics for today. The first topic is something called device efficiency. Yeah, that's it. Yeah, the topic for a little while now is called device efficiency. Now we've had this topic of efficiency before, but it was for cycles. Do you remember we had we had a cycle like to to refresh your memory here, this is called a power cycle. And this is a high temperature. See if this rings any bells. This is a low temperature. And this is your output power. This is your heat transfer rate at the low temperature. This is your heat transfer rate at the high temperature. And that thing right there is called a power cycle. There's another name for it. The other name, oh gee, did I leave my water jug? I bet I did. Huh?
Downstairs, I'll go get it.
Oh, no, it's right there. It's right there.
Oh.
Yeah. Thank you so much. The other name for a power cycle is a heat engine. But you need to know how to work those. There were three kinds of those cycles. There were power cycles, heat pumps, and refrigeration cycles. And on your final someday, we'll have to have one of those for sure. But they had an efficiency, and it went like this. In this case here, let's put some numbers in here. So suppose this was 20 kilowatts. And suppose this is 14 kilowatts. And this would have to be 6 kilowatts because 14 and 6 add up to 20. And the efficiency of this cycle, I'll give you 30 seconds to figure it out. You now have 25 seconds. Wonder what the efficiency of that power cycle is. The other name for power cycle is a heat engine. It's the efficiency of a cycle. And I'm getting 70%. I wonder if I did that right. Because see, the efficiency would be the output, which is 14, divided by the input, which is 20. Yeah, I think that's 0.7, isn't it? Math students, how'd I do?
It's correct.
Yay! That's the efficiency of that cycle. But now we're not doing cycles today. We're doing devices. The topic right now is device efficiency. See, they can have efficiency too. So I'm going to erase this now that you understand that. Okay, say goodbye to the power cycle there. Now, the efficiency of, there's all kinds of devices, like there's turbines and compressors and you name it, and throttles. Yeah, throttles. What else is it? There's all kinds of devices, but we're just going to do turbines today. Now the device efficiency for a turbine, we'll put a little T there for the turbine. And what it is it's the work per mass, the actual work per mass that you get, that you get from your turbine, divided by the reversible. See if the thing runs, if your turbine runs reversibly, well, there's no bad stuff that decreases your efficiency. There's no friction, for example, and you get a bigger, you get more work per mass. You get more work, more power. That kind of makes sense. Okay, well, we're going to do one. Now, let me see if I can find the one I wanted here. And this one is problem, this is an example in your book. Let's go through it. We're going to do example 711. It's on, in my book, it's on page 227. Okay, let me find it and we'll just go through it. It'll be fun. Page 227. I found it. It's a steam turbine. It's in my book. It's on page 227. And so here we go. We all know that when you do our problems in this class, you draw a device sketch. So here goes. Here's your device sketch. We're doing our device sketch now. And let me read what it says. It says steam. Okay, well, I'm going to put H2O here because we're dealing with steam. Pressure comes in at 1 megapascal and 300 Celsius. 300 Celsius. The steam leaves the turbine at a pressure of 15 kilopascal. The work output of the turbine is measured and found to be 600 kilojoules per kilogram. And they want the turbine efficiency. Now we got to decide what this is, this 600. I tell you what, here's your choices. It's either big W dot, little w, or little w dot. It's one of those. And you can always tell what things are by their units. See, this here would be in kilojoules. This here would be in kilowatts. This would be in kilojoules per kilogram. And this would be in kilowatts per kilogram. You can tell what stuff is by the units it's in. So guess what we got? 600 kilojoules per kilogram. Hey, I know what that is. That's a little w, isn't it? Yes, it is. So we now know that that's the output work per mass. You don't need this stuff anymore. And now what we're going to do is we're going to try to get all of our properties. So go to the back and find water. Hey, if it's water, you use the tables. So we're going to go back here and we're going to, we're looking at water. And now, do we want English or do we want SI? What do you guys think? English or SI?
SI.
We want SI. So I'm going to try to find 1 megapascal. I'm hunting through the water table now. And by Jove, I found it. We need 300 Celsius. Okay, I'm going to list my properties now. Now, little v1, I'm getting 0.25794. And I hope that some of you are looking, you know, my little V there is, I've got pictures of you guys. It's kind of in the way. Let me, Maybe I should write that over. That's a little V1. On my screen, I've got pictures of you guys in the way there. I hope you can see it okay. But maybe I need to split this. Let me see. What if I do? Yeah, there we go. Now you can see it maybe. Okay. Let's do a little H1 here. I hear some screeching.
That's my son. I'll mute it here in a second.
Well, thank you. That's fine. H1, now let me see, where was I? Okay, here we go, yeah. And we need 300. There it is, an H1. If I make a mistake, somebody speak up, but I think this is 3051. 51.15. All right. And S1, we're going to do S1 now. S1 is 7.1228. Okay, well, we got all the properties coming in. But what about going out? Well, we do know it's 15 kilowatts, or I'm sorry, kilopascals. Okay, well, my mind just sort of blew a blank just now. We're going to have to do the first law of thermodynamics is what we're going to have to do. So let me write it. Here we go. First law. Now you know how it goes. It goes like this. Now I think they didn't say anything about velocities, did they? So I think you can just forget that. There's only one inlet. Now, on this equation, this is 0 because it's steady state. This turbine's been running all morning long, and the energy inside hasn't changed with our passage of time. Properties can change with location. See, the pressure changes from 1 megapascal to 15 kilopascal, but that 15 kilopascal stays the same all morning long. It doesn't change. That's the output pressure. So this is 0. It's a steady state deal, and we're just going to assume it's adiabatic. Turbines really aren't, but that term is negligible compared to this term. This term is called power, and it's not negligible. It's the reason why you have turbines. But what I'm going to do here is I'm going to divide through by m dot, and that'll get rid of those m dots. And when you divide big W dot by m dot, what you get is little w. And the m dots go bye-bye. And you got this nice equation here. And looky here, we know what this is, and we know what this is. What does it mean in this class when we circle something? It means we know what it is. Yeah. Okay, well, we can find H1 then. You guys all have calculators. Get them out. No, not H1. I mean H2. We know what H1 is. But see, you can solve for H2 now. Go ahead. I'll give you one sip of water, enough time to get that.
I might be missing it, sir, but wouldn't we need to? Oh, actually, never mind. Sorry. I was thinking we needed to find T2, but we know the work in H1, so I'm an idiot. Sorry.
We're going to find T2. Eventually, we will get, see, we don't know what the exit temperature is, but we're going to get it. Just be patient. Well, I did that, and I tell you what I got for H2. I got 2451, blah, blah. Kilojoules per kilogram. And I bet that's what you got. Well, so what? Now, if you read the problem, for those of you that just tuned in, we are doing example 711 on page 227. That's what we're trying to do. And if you read the problem carefully, that's always a good idea to read the problem. And it says, never mind. I thought it was something else, but I'm okay now. All right. Well, we got that. So what? All right. Now here's what we're after. We're after the device efficiency, and what that is that the actual work over the per mass, that's a little w, divided by the work per mass if the device was reversible. If it was reversible. Well, this device is not reversible. And look at here, we know what this is.
Sorry.
But that's what this is. This is the actual, that is the actual work per mass. If we could only figure out this right here, the reversible work per mass, we could solve for the device efficiency. That's what we need to figure out. Now, how are we going to do that? Well, we're assuming that this turbine is adiabatic. And if it's reversible and adiabatic, we have a special name for that. Let me write that down. If you have an adiabat that's also, that's my ampersand sign. If it's also reversible, they have a name for that. It's called an iso something or other. Does anyone remember what that is if you have a reversible adiabatic process?
Is it isentropic?
That's it. Ta-da, good going. It's an isentropic process. Excellent. We have an isentropic. You know what an isentropic process is? It's when delta S is 0. That's what it amounts to. Let me show you why. I'm going to write the second law of thermodynamics now, and I'm going to show you that. I'm going to erase some. I need this room here, but I'm going to write this H2 here in case we need it. I don't want to put it there, though. I need to put it down here someplace. H2 is 2451.15. All right, I'm going to write the second law. Here goes. And we don't need all this stuff. I want to keep that, though, I think. Yeah, we'll say goodbye to all that. That's your first law. Now I'm going to write the second law. Now, keep in mind now, this is a control volume. It is not a control mass. It's a control volume. And the second law of thermodynamics for control volume looks like this. It's in your book. These would normally be I, MI, and ME, but they happen to be the same on our problem here. There's just one inlet and one exit. There you have it. That's your second law of thermodynamics. And now this here, the change in the total entropy inside your turbine with respect to time is zero. Do you know why it's zero? You know why? And no, those are good, intelligent guesses, but it's zero because it's steady state. Nothing is changing with time. The total entropy or any other property inside your turbine does not change with time. Okay, now somebody said adiabat. This is zero because there's no heat transfer rate. There's no heat transfer. That's zero. Now this one's zero. How come this one is zero? By the way, that needs
Reversible.
Huh? Yes, I heard that. It's reversible. Very good. And can you see that you could take that m dot, since they're the same, and do a little algebra trick here? Hey, you know what? The only way that's going to be zero is if these are equal, because m dot's not zero. So the bottom line is the incoming specific entropy is equal to the exiting specific entropy. Well, that's what I was telling you up here. The name of this is an isentropic process, and the incoming entropy per mass is equal to the exiting entropy per mass. Well, I wanted to make sure that you understood why. Let me erase that, and we're going to use that now. Here goes. Any questions on that so far? Well, I didn't hear anything. Okay, we'll say goodbye to that for now. Now, here's what we know. We know that S1 is equal to S2 because it's a isentropic process. And we know what S1 is. Hey, look at here. S1 is 7.1228 kilojoules per kilogram Kelvin. Now we know what S2 is. We've got another property of the exit here. It exits at 15 kilopascals, and it has a specific entropy of 7 point blah, blah, blah. When you have two properties like that, you can find all the others. We're going to find all the others. Go ahead.
I was saying I think it's going to be saturated.
You know what? I think you're right. Very good thinking. We're going to go to our water table now, and we're going to look at 15 kilopascals. Let me see if I can find that. It is going to be saturated. Good thinking, Batman. There is no, in the superheated vapor region, there is no 15 kilopascals, but I think it's saturated. I don't think it is super heated vapor. So we're going to go to 15 kilopascals. And here's what it says at 15 kilopascals. I'm looking up, there it is. It says the entropy, of course this would be at state 2, is equal to SF plus the quality at state 2 times SFG. Now we know what this is. We can look these up in the tables and we can get the quality at state 2. Once we get the quality at state 2, we can get the other properties. So let's do it. Here goes. This is 7.1228. And at 15 kilopascals, that's 0.7548. We're going to get the quality at state 2. Remember what quality is. It's the percentage vapor that you have, plus, or times, 7.2536. Now we're going to solve for the quality at state 2. I'll give you 30 seconds, maybe even 40 seconds. Go for it. Okay, your 30 seconds or whatever is up. Did you get the quality at state 2 to be 0.8779?
Yes, sir.
Yay! Good going. Now with that, I think we can get some of the other properties. But let's just wait a minute for anybody to catch up.
I got it.
Yay, good going. Okay, now I wish it had all of your names over here. I only see just a few. I don't know how to do that. My daughter just went away. Okay, now I need some room to do this in, so I don't need that right now. And in fact, I don't need that because we figured it out. I got a little room here. We're going to get the, we can get the specific volume at state 2. And you know how the equation goes. It goes VF, let me find that, at 15 kilopascals. You guys could do that. I'm too lazy to do it. What we really need is this. We really need this specific enthalpy at state 2. And what that's going to be is HF. Let me find it here. It's 225.91 plus the quality, which is 0.8779 times HFG at 15, which is 2599.06. And see, we can get the specific enthalpy now at state 2. I'll give you another 30 seconds. Go ahead and get that for me. Okay, great. I think we got 2309 point 3.
Yes, sir.
Yay, good going. That's the quality, or not quality, that's the specific enthalpy at state 2. If you had an isentropic process, see, that's what we're after. We're trying to find the work per mass if you
I
have,
got a different answer.
let me do it again.
7.
I got 2,507.
Okay, now,
That's what I got.
okay, now just a minute. I'm goofing up here, and I really appreciate you chiming in there.
The 2599 number, I think, is HG. I think you need to write down HFG, correct?
Okay, now just a second. We'll get this. Just bear with me here. I got this 8779 right. That's right. And I think the 225.91, I think that's right. What we're fighting about is this right here right now, isn't it?
Yes, sir.
And at 15, that's wrong. That is wrong. And whoever just told me that, big honking thank you point for you. This should be 2451.56. And I did, if you do that, that's the right number. I think you do get this.
And 2373.14, sir.
Okay, just a minute. 50. It's 2373.14. I don't know, where did I get that number from? Where in the heck did that? I don't know. You're absolutely right. It's 2373.14.
And you calculated it. You did it right, though.
I got this
Right
right.
numbers.
I got this right, but I kept putting in the wrong numbers here. Here's another thank you point for this wonderful class. I think we got H2 now, finally. I hope I didn't confuse too many people. Now what I'm going to do is I'm going to write the first law of thermodynamics for the isentropic turbine. Now we don't have an isentropic turbine, but I can pretend we do. I can pretend we have an isentropic turbine. Isentropic process. The real process, there's H1 and where's H? Yeah, there's H2. There's the H2 for the real process. We figured it out. But see, for the isentropic process, the H2 is this here. Now we're going to write the first law, and here it goes. Now you've seen me write this over and over again. Can I be lazy and just put a 0 here because it's steady state, and a 0 here because it's adiabatic, and a 0 here if it's an isentropic process? There is no entropy generation. And because I probably shouldn't short circuit this thing, but what this amounts to is H1 minus this. What this is the H2 for an isentropic process.
That's for the first law, right? And
This is the first law.
I think it has to be like the power.
We divide through by the m dot and we get rid of the powers.
And
I probably shouldn't have done that shortcut.
we need the work, right? So
We need the work of the
It's not
reversible turbine. Maybe I can go back.
it's not 0.
What's
Is
that?
it 0? Is it 0? The work is the work 0?
No, the work is not 0. Now just a minute now. It's not 0. I was wrong. I think that was Coy, wasn't it?
Yeah.
Thank you, Coy. Now this is the work of the reversible cycle. I just don't have enough room. If I had a little more room, I'd be a lot happier. But here we go. We can solve this now, and we can find this because we know H1. It's the same. Where is it? Here. It's right here. Put a fence here between that and that. That's totally separate. H1 is 305,115. And this H2, I put an S there for constant entropy for the isentropic process. And then we think it's this here. We're going to subtract 2309.3. And what we get is the work for the reversible process is 741.85 kilojoules per kilogram. Now we have this, and we can find the device efficiency. I tell you what it is. It's 600 over 741.85. I wish I'd had room to write that out and explain it better. But if you'll divide those, what you'll get is, I'm getting 0.8088. That is the turbine device efficiency. Now we're going to write the TS diagram here in just a minute, but let me see what the book said for their answer. Now we did an example. They have an answer. Look on page 227. 227. They said that H1 is 3051. Did we say H1? Yeah, look. They said H1 is 3051. That's what they said. They said S1 is 7.1228. That's what we got. I just put a line there to sort of separate those. They said the specific entropy at state 2 is the same because it's isentropic. It's 7.1228, just like it doesn't change. It's constant entropy. They said that. And then what they did was they found the quality. They found the quality, and they got 0.8779.
We did as well, sir.
Yeah.
I don't know if you still have it up there, but that's what we had.
Did I erase that part? I must have erased that part.
Oh, it's down in the bottom. Very bottom.
Well, how did we get the 0.8779? I don't see that. I think we erased it. Oh no, there it is. I'm getting lost now.
I think we found it with H1.
Yeah.
We found it using
Yeah, we
S,
found it. We
S2.
found H2. We know H1, we know H2, and we found that quality.
By going down to 15 kilopascals and using H2,
Yeah.
I believe.
Well, we're in agreement with everything so far. They found the work by the what they call it, isentropic turbine is 741.9. They rounded off. And then they divided 600 by 741.9, and they got 809. Well, that's pretty close to what we got. Now let's draw the TS diagram. I need some of these values to do it. Well, they're right here in my book. I can look in my book, but I'm going to try to draw the TS diagram now, because that's part of the deal. You draw a device sketch, and you draw a PV and a TS diagram. Now state one, I think, didn't we locate that in this superheated vapor? Yeah, it was in the superheated vapor. Now look at here. This is a TS diagram. I know the top of this is 374. So 300 degrees Celsius is like that. But we're in the superheated vapor. We're out here someplace. There's state one. Now it's at 1 megapascal. Now the way isobars go is like this. This is let's write it as 1,000 kilopascal. There it is. See, there's state one. And this is 1,000 kilopascals. Isobars are kind of funny on a TS diagram. That's how they go. And we have an irreversible process that took us to 2451. Well, I think 2451 is still in the saturated region. So what that means is we came down here, we'll draw a dashed line, and there's state two. How do I know it's inside here? Because if you look up Hg at, what's the pressure, 15? At 15, okay, now how does that go? Yeah, 15 kilopascals. What does it say back in the table? 15 kilopascals, and the specific enthalpy at 15 is 2599. This value right here is 2599. And what we have is 2451. Well, you know what? That's smaller than 2599. So we're inside. See, here's your 15 kilopascal isobar. There it is. This is your actual process. And we'll draw it with a dashed line. By the way, they don't do it. If you'll notice, if you'll read your book here, they don't have the TS diagram or the PV. But you guys always know that you need to do that. But now we're going to do the, what's the word? The isentropic process. Now that's when delta S is 0. So what that means is this comes straight down into 15 kilopascals. I think I call that 2s. The S stands for constant entropy. There's state 2s. And it's got the same entropy as state 1. Uh-oh, I erased it, didn't I? It's 7.1. Well,
10.1228.
Thank you so much.
No, wait, that's specific volume.
Oh. Well, that's entropy, isn't it? No, that's right. I think we did that right. Let me double check. I don't want to.
Oh, you're correct, sir. You're correct.
Well, okay.
That's
See, in fact, we can put it on our graph right here. This value here is 7.1228 kilojoules per kilogram Kelvin. That's your specific entropy. It's state. It's not here at state 2. It's here. it's state 2s. I call it that because this is your isentrope. They call this an isentrope. It goes straight down. Your change in entropy is 0. S1 and S2 are the same. 7.1228. There you have it. But you see, the actual process does that. Now, if you wanted to do a PV diagram, we could. You guys are more familiar with PV diagrams. I bet you could do that. You know you're going to go from superheated vapor to saturated mixture. But both diagrams are going to lean to the right. Well, we've just talked about device efficiency, and I want to go on to the next topic. And I'll give you guys some homework, but don't turn it in. Hey, I finally caught up on my homework, and my daughter's going to help me. Here, I'll stick my nose in here. My daughter's going to help me find a way to grade your homework and record it efficiently. I'm just not there yet. But I'm going to give you homework. I want you to do it because I want you to learn how to do this stuff. Okay, now the next topic. That was device efficiency. The next topic. Is there any last comments or questions on device efficiency?
No, sir.
Well, okay. Now that's for a turbine. Let me just mention that all devices have efficiency. Guys, I was going to erase that with my mouse. That's where I'm at. See, did that tell you anything? I was going to erase that with my mouse.
It might work.
Here, let me tell you about at least another device besides turbines. There's also compressors. I think we've done compressor problems. But the device efficiency for a compressor it's like this, only it's upside down. It's the reversible work divided by the actual work. Now the reason is because you got to put work into a compressor, and if it's reversible, this will be smaller. And if it's got friction and a lot of other bad things happening, the work you got to put in will be bigger. And so you'll always come out with something less than 0 for the efficiency of a compressor, because this will always be smaller than that. Notice it's just upside down. For a turbine, it's the actual over reversible. For a compressor, it's reversible over actual. And all of the other devices have efficiencies too, but if I ask you a question on your final, it'll be a turbine. Okay, now the next topic, unless there's a comment or question. All right. Well, I'll tell you one more. Nozzles have, we're going to talk about nozzles because that's a favorite. Nozzles are a favorite test question. We could put one on your final. But if you wanted the efficiency of a nozzle, what it is the kinetic energy, the actual kinetic energy that you get with the actual real life nozzle divided, this is for nozzles, divided by the kinetic energy if you had a reversible nozzle. In other words, an isentropic. If you had one of these kind of nozzles where the change in entropy going in and out is the same, it'll go faster. Do you remember the purpose of a nozzle is to speed up? It's to speed up. And if you have a reversible nozzle, it speeds up more than the irreversible. It kind of makes sense. Like friction is a big cause of irreversibility, and that slows you down. Friction's going to slow you down. And it'd be fun to work device efficiency on nozzles, but we can't do everything. But the topic today is nozzles. And I'm going to do a nozzle problem. So let me say goodbye to all this stuff. For now, we did device efficiency of a turbine. And my daughter's fixed it to where this is recording, and she's going to put it on YouTube. And there's a way that she can post this, I guess, on Blackboard. I don't understand, but there's a way that you guys can watch this video over and over and over if you want. Isn't that great? Great. Yeah, really good. Yeah. Okay. The topic right now is nozzles. And let me see what I'm going to do with nozzles. Let's see here. Again, I think I'll do an example. I'll give you some homework though. Let's see where did I put that? Sorry to take up your valuable time there, but I need to find where the homework is. I'm going to give you guys. Ow, I just hit my elbow. That hurt. Ah, hit my elbow. Okay, yeah, here we go. Yeah, I'm going to give you this problem here. So now I know what I'm going to give you. Good, excellent. But we're going to look at a reversible adiabatic nozzle. Now this is also an example. It's a 7.2. Do I want to do the English one? Or do I want to do the SI one? You got to know how to work in English, people. So let's do the English one. Now what this is example 7.2e. Let me find it. Hang on. 7.2. Yeah, there it is, 7.2e. We are going to do example 7.2e. It's English, senor. See that E? It's English. And it's on page 210. Now we've had nozzles before. And here's what you have to remember about nozzles. Well, you need to know the first law, for sure. The first law for nozzles goes like this. There it is. And I know I've given that to you before. Now let's read our problem. It's, now wait a minute. Don't we have to draw a device sketch? Let's draw a device sketch. And what do we got going through? Oh, it's steam again. All right. I'm on page 210 right now in my thermo book. And we're doing example 7.2e. And I've drawn my device sketch. We know it's water. Now I'm going to write down what we know about it. Ooh, it's a reversible adiabat. They said we have a reversible adiabat. Now, we have a special name for that. It's one word. It goes ice and something or other. And it is the reversible adiabat. It's an isentrope. I get the feeling of deja vu. Didn't we go through this a little while ago?
Yes, sir.
But see, I'm a believer in repetition. I don't get things the first time through, and maybe you're human. Maybe you have to be reinforced a little bit. This is an isentrope. And I showed you why, because I wrote out the second law of thermodynamics. And when we got through, we found out that the entropies going in, whatever it is, call it S1 maybe, is, well, per mass, is going to equal the entropy going out if it's a isentrope. So that's good. Now let's write down what we know here. Coming in, let's see, steam comes in the nozzle, 100 psi. So let me write down some stuff. We got 100 psi coming in at 500 Fahrenheit. 500 Fahrenheit. A velocity of 100 feet per second. 100 feet per second. Pressure of the steam at the nozzle exit is 40. Let me write that down. This is 40 psi. They want to know the exit velocity. And they told us it's a reversible adiabat. So I tell you what let's do. Let's go ahead and get the other properties. Now we need English, senor. So I want you to go to where they have Fahrenheit and PSI and all that stuff. There it is. And what we want is 500 Fahrenheit. Okay, getting close. 500 Fahrenheit. Well, that's not at the top. Let's do a PV diagram, sort of orient ourselves where the heck we are here. We're going to do a PV diagram. See, the top of this is, gosh, it's 22 megapascals. We only got 100. We're way down low. We're way down here someplace. 100 psi, 500. But you know what? The top of this is at 705 Fahrenheit. So 500 is sort of like this. Kind of faking this. Then it goes flat. And there's your 500 Fahrenheit isotherm. And we're at 100 psi. We're way the heck over here someplace. Here, let me fudge this just a little bit so it doesn't go forever. Okay, now come over here. Ding. there's state one. We're at 500 Fahrenheit and 100 psi. And let's write down, it's superheated vapor, isn't it? And let's go to the superheated vapor chart and let's look up 100 psi and see what the other properties say. It says here 500 Fahrenheit. The specific volume is 5.5866. I hope you guys, somebody out there is checking on this. We've already got 3 thank you points. You guys are so good. Wonder if I got that right. Now let's get the specific enthalpy. It's state 1, and it is 1279.10. That looks pretty good. Oh, that first one. Do I need to move this over just a tad? There we go. All right, great. Specific entropy, let's get that. What have we got? 100 psi, yeah. And we need 500 Fahrenheit. 1.7085. 0.7085. So far, so good. Now, what do we know about state 2? Well, we know that the specific entropy at state 2 is equal to the specific entropy at state 1. So we know what it is. It's 1.7085. 1.7085. Probably should write the units down there. Now, you know what that is? That's BTUs per pound mass Rankine, isn't it? Kind of weird. Let's see, we got some wonderful students here. I see Andrew and Miranda and Coy. Good going. If anybody tuned in late or took a little nap, we are studying nozzles, and we are studying example 7.2e in our book. That's what we're trying to do, 7.2e. And we have tried to write a PV diagram, but what about state 2? It's at 40. You know what? 40 psi is down here. It's smaller than 100. So it's down here someplace. I get the feeling state 2 is down here someplace. We haven't got the info on it yet, but we're going to. That's what we're going to do right now. I tell you what we know. We know that the pressure at state 2 is 40 psi, and we know that the specific entropy at state 2 is 1.7085.
Probably around 300 degrees Fahrenheit. Looking at the tables at least.
You know what? That's dang close. What I got was 314.2 degrees Fahrenheit. So you kind of eyeballed the table.
Yes, sir.
Pretty close. But let's go ahead and get it exact. And here's how you do it. You go to the table and you look up 40 psi, because we know that. So let me find that. I'm snooping around now, trying to find 40 psi. And 40 psi. Got lost there. Let me keep looking. Hey, by Jove, I found it. I've got 40 psi. But see, what we want is a specific entropy of 1.7 blah, blah, blah. Well, they don't have that. I tell you what they do have. Let me write it down for you. They have a temperature, specific volume, specific entropy, or enthalpy, I mean, specific entropy. I tell you what, we want 1.7085. It's between these two. It's between 280. I'm writing this from the tables, guys. I hope you can find this. And this is 10.711, and this is 1176.59. And this is 1.68. I'm getting this from the tables. 1.6857. And the next one down is this one here, 1.7124. And this is 1196.9. And this is 11.360. And this is 320. We're going to have a process like that. But see, what we need is these values in here. Now, we know what the specific entropy is. It's the same as it started. It's an isentropic deal. It's 1.7085. And you guys all know how to interpolate, so I won't bore you out of your gourds. Here's what I get, 1193.93, 11.265, and 314.2 Fahrenheit. See, I had to interpolate that table to get it. And here comes your 314. Yeah, here comes your 314.2. It goes like this. Comes up here. And then it goes here. And then, this is 314.2 Fahrenheit. And see, this is 500 Fahrenheit. And we have just plotted the process. Notice I have a state 1, a state 2, and I have my process drawn between them with an arrow tip. I need to see that arrow tip. We're going to go from 1 to 2. It's kind of messy there. Okay, now we did all that. So what? Well, what are we supposed to find? I think they want us to find this velocity coming out the end. Okay. Well, let's keep track of all the stuff we know. We know what H2 is. Let me make a little room here. We know T2. T2 is 314.2. And here's H2 right here. Here, I'll write it here. H2 is 1193.93. 1193.93. Now what we're going to do is we're going to fill in this equation and get our answer. See, we know what H1 is. Look, there's H1, and they gave us V1. We know what that is. Look, there it is, 100 feet per second. H2, it took us a lot of effort, but we got H2. It's 1193.93. we should be able to solve this. See, this is what we're trying to solve for right here. Put a little mystery cloud around it. We can do it, can't we? Okay, well, I just need some room to do it. Let me do it up here, okay? You guys all know this equation. Memorize that equation. That's the first law for nozzles. Let's put a nozzle on your final one of these days. So I'm just going to put the numbers in now. Here goes. We'll get rid of that for now. We know we're studying nozzles. Now look at all the room I got there. Isn't that great? Okay, I'm going to write down all this stuff, and we're going to find that exiting velocity. We know H1, it's 1279.10 BTUs per pound mass. Hold on, we got that. Gosh, I've only got you guys theoretically for another 15 minutes, huh? That's okay. I think we can get done with this. I can give you the homework, and then we'll meet again on Tuesday. We're going to meet every Tuesday and Thursday. And when I can figure out how to do it, my daughter, she's right on the verge of it. You can watch these over again if you miss one. Okay, there's H1 plus V1, which is 100 feet per second. It's V squared over 2. But see, that's not BTUs per pound mass. To get BTUs per pound mass, you got to do some fancy-wancy conversions here, but we can do it. And what you have to do is you have to multiply by a foot-pound force is 32.174 pound mass feet per second squared. If you've forgotten that, it's in your book. I think it's page 20. Let me look it up here. Let's see. No, it's not page 20. And maybe it's page 9. Let me look on it. No. Yes, it's on page 9. That conversion right there is on page 9 if you don't remember it. But Matt, we're still not at BTUs per pound mass. But look at here. A BTU is 778 foot-pounds of force. Foot-pound, yeah, there you go. And that will get us in the BTUs per pound mass. You get BTUs per pound mass. See, the foot squareds per second squared, they will cancel, I think. Just a minute now. Let me think about this. Yeah, see that foot-pound force, they cancel, don't they? Yeah, they cancel. And you see that foot squared, second squared, and that foot second squared, it almost cancels, but you're left with a foot though, aren't you? Oh gosh, did I do that right? Just a minute here. I think it's right, but I just don't quite see it yet. That foot-pound, where did this foot-pound come from? No, that doesn't belong there, guys. A pound force is equal to 32.174 pound mass feet per second squared. That's on page 9. Now it works. See, you'll have a foot-pound, which cancels with a foot-pound, and you'll have BTUs per pound mass, which is BTUs per pound mass. You're okay now. I had a mistake there, but I fixed it. Okay, now this is equal to, it's equal to your final specific enthalpy, which we figured out is 1193.93. It's 1193.93 BTUs per pound mass plus V2 squared over 2. But to get the units to work, you got to multiply, or no, you have to divide by 32.174 and 778. Got too lazy there, but I wrote the units there. Now look at that. It's ugly, but you have an equation with one unknown. Now I'm going to shut up for a minute or two, and I bet that some of you can get the answer. Get your calculators out. Never mind all the units, we figured those out, but don't forget the numbers. And don't forget the numbers, and solve for your final velocity. On your mark, get set, go. Oh. Okay, well, I don't know if that's enough time to do that. It's kind of ugly. Let me start from scratch and see if I got the same answer I did last time. I hope you can read my writing. That's a 778 right there. Yep. I get the same answer I got the last time, I think. Yeah, I did. Hey, I got the velocity of the exit. The exiting velocity is, now I got 2067 feet per second. I'm calling out to my wonderful students. Did anybody get that?
Yeah, I got that.
Yay, there's two of us.
Yep.
Yay, there's three of us. Fantastic. Now, if you didn't get it, write it down in your notes and grind it out. Is there any question on anything that you want to ask me about? I just don't want to screw up and erase this recording. See, this is being recorded, and there's a way you can watch this all over again on YouTube. My daughter's going to help me. In fact, I'm going to go get her. I'm not going to screw this up. She's going to be the one to help me log out. But I'll answer any question that you have.
When you do want us to submit homework, would it be all right just email you a picture of our papers, or?
I don't know how to answer that yet. Let me talk to my guru daughters. They're really good. Well, see, they're young people like you guys. See, when I was a child, there was no such thing as all this. We played in the dirt with rocks and sticks. That's what we did. Okay. But I'm getting there, guys. Just be patient with me. I am getting there, and we will find a way to submit homework. Here, we'll get my ugly mug in here. There you go. We will find a way to submit homework efficiently, but I'm still listening. Did you have any other comments or questions, anyone? Okay, well, I will see you guys at 9:30 on Tuesday morning, I guess, right? That'll be good.
That'd be the strengths class, wouldn't it?
Oh, that's right. I mixed up. Yeah. I'll see some of you then, but the rest of you I'll see at 1. I need a couple of hours between my classes to think. So we're having strength at 9:30 and thermo at 1. Thank you for being patient. We can do this. I'm going to go get my daughter to log this thing out. Bless each one of you. And it's Easter weekend. He is risen. This is going to be Good Friday tomorrow, I think. So, adios, muchachos.
Goodbye.
Thank you, sir.
Goodbye.
Hi, Professor Griffin. See you next week.
Yeah, see you next week. Yeah,
Bye.
great. I'm going to go get my daughter. Hey, Susanna. Come and log me out so that I don't erase the universe.
All right, so you're done now.
Here, let me get over to where I can watch you.
Okay, so we're just going to end the meeting.
Yeah, now wait a minute. Now oh, you just wiggled it till it says end meeting.
Uh-huh.
Okay, now. Yeah, now here's where you got to be careful now. I don't want to screw this up. It says end meeting for all. What do you think? End meeting for all.
Let's see. See, are those people still on?
I don't know. Are they? No, that's you.
Yeah, but
That's-
these people.
Oh yeah, they're
Oh, but
leaving
they're
us.
getting off now. Okay.
They're leaving us now. Hey, there's Ethan. Hi, Ethan.